1 billion years before the present, Earth wears a different face. Continents cluster into a supercontinent in the making. Seas are rich in iron, but poor in oxygen. The sky glows under a dimmer sun. And life, mostly microscopic, is rehearsing new tricks it will later unleash on a grand scale. This is not prelude. It is a chapter where the rules of atmosphere, ocean and biology lock into patterns that will shape every future world. Start with the clock. A day is shorter than today, about 19 to 20 hours, because the moon orbits closer and Earth spins faster. Tides run stronger, twice daily pulses that rake continental shelves and stir shallow seas. The sun's luminosity is lower by a few percent, but greenhouse gases and cloud patterns keep the planet from freezing. This balance is delicate, a dance among volcanic outgassing, weathering of rocks, and the chemistry of the oceans. If you could stand on a shoreline, the horizon would look familiar. Blue water, scattered low islands, but the air and the sea beneath would not be yours. The continents are converging toward a configuration geologists later call Rodinia. Think sweeping collisions instead of quiet drifts. A long future. North America's eastern and southern margins crust buckles in a mountain-building saga known as the Grenville orogeny. Rocks that will one day underlie the Adirondacks and the Canadian Shield are shoved and heated, metamorphosed into banded gneisses and hard, glittering schists. Far inland, the crust in the continent's heart will soon begin to split in a failed rift, pouring out dark basalt along a scar that future geologists name the Midcontinent Rift. Supercontinents are not tidied puzzles, they are stitched from scars. Supercontinent interiors dry out. Imagine vast highlands shedding dust into inland basins, while coastal margins host broad, shallow seas. Those epicontinental seas, warm, sunlit, and slow to mix with the open ocean, become chemical laboratories. The surface waters, flushed with sunlight, host swarms of cyanobacteria and protists. Below the photic zone, oxygen vanishes and the water turns ferruginous, rich in dissolved iron, or sulfidic along certain shelves. Where free sulfide accumulates, it poisons many metabolic pathways. Life adapts by retreating upward, by migrating along chemical interfaces, or by evolving metabolisms that tolerate toxic edges. The atmosphere holds less oxygen than today, far less. After the earlier great oxidation event raised oxygen from trace to modest levels, the planet settled into a long plateau, sometimes called the boring billion, from roughly 1.8 to 0.8 billion years ago. The nickname is unfair. Stability can be dramatic when you zoom in. Oxygen likely sat at a few percent of present atmospheric levels. Fires on land are impossible because there's not enough oxygen to sustain them. Lightning may spark dry storms, nothing burns. Nitrogen dominates the air. Carbon dioxide is present at concentrations higher than modern, but not enough to overwhelm climate by itself. Methane, once abundant, is controlled by oxygen and microbial sinks. The chemistry is a tug-of-war among volcanoes, weathering and biospheres that are learning to breathe the planet's new air. Life exists everywhere. Liquid water and energy gradients persist. On tidal flats, microbial mats trap sediment grains day after day, season after season, building laminated domes, stromatolites, that break the wind and ripple the shallows. Crack one open and you'd find fine alternating layers, light bands where photosynthesis thrived, darker bands marking nights and storms. In deeper waters, the planktonic world diversifies into acritarchs, cell-walled microfossils with spines and ornaments, the pollen-like confetti of early eukaryotes. Among them are milestones, red algal fossils such as Bangiomorpha, early candidates for complex multicellularity and sexual reproduction, appear in rocks a little older than 1 billion years and persist into this time. Sexual cycles shuffle genes and accelerate evolutionary experiments. Complexity is not visible to the naked eye yet. It is real in the life cycles of cells. Follow a river from mountain to shelf and you can watch the planet's engine cycle metals and nutrients. Weathering of uplifted Grenville belts delivers phosphorus and trace metals downstream. Where those nutrients meet light, productivity blooms. Where productivity excels, oxygen is generated. And where organic matter sinks into anoxic depths, iron and sulfur react to lock away elements in minerals. This coupling between tectonics, chemistry and biology is the Proterozoic signature. It sets feedbacks that keep oxygen low enough to maintain anoxic deep oceans, but high enough to sustain a surface biosphere that continually feeds itself. At night, under low-latitude skies, auroras can snake farther from the poles than they do today. Earth's magnetic field, generated by a still-cooling core, deflects the solar wind, and charged particles precipitate where field lines guide them. With different solar and atmospheric conditions, the colors and latitudes of the lights drift. Over millions of years, the magnetic poles wander. Sometimes they flip. Lava flows capture these flips as bands of remnant magnetization, natural tapes that future geophysicists will read to time motions of plates. Seafloors are younger than continents, and they tell time in stripes. Mid-ocean ridges, upwelling centers where mantle material cools and spreads, feed oceans with heat and chemicals. Hydrothermal vents gush metal-rich fluids into ferruginous seas. Iron and silica precipitate as shimmering flock, painting the near-vent seafloor with chemical snow. Microbes colonize these gradients, building ecosystems without sunlight. Vent chimneys rise and collapse, repeating the story as long as heat flows. In these deep realms, life never sees the sky, but rides the same laws of physics. Thermodynamics prefers order locally when energy pays the bill. 1 billion years ago is also a lesson in patience. Evolutionary innovations that will later dominate, skeletons, shells, predation, burrowing, are rare or absent here. Instead, the stars are cellular, organelles refining cooperation inside eukaryotic cells, cytoskeletons and membranes testing shapes, sexual recombination spreading useful tricks through populations. The quiet before the Cambrian is not empty. It is a slow build of biochemical and ecological potentials. When oxygenation pulses upward and ecosystems stratify differently hundreds of millions of years later, those potentials will explode into form. Look again at the continents. Their assembly into Rodinia rearranges ocean currents and climate. Supercontinents alter the albedo of the planet and the efficiency of chemical weathering. When continents cluster near the equator, tropical storms wring heat from seas and deliver heavy rains onto rock, accelerating the drawdown of carbon dioxide through silicate weathering. When they sit at higher latitudes, ice sheets, if any can form, would reflect more sunlight. Today's Earth knows ice. This Earth does not carry permanent ice caps, but it remembers how to make them. In the next chapter of Deep Time, as Rodinia rifts and geography shifts, a cascade of events will tip climate into global glaciations, Snowball Earth episodes that grind continents and push life to the edge. Those are still ahead. For now, warmth holds. In this world, a shoreline morning would greet you with tides lapping over microbial carpets, salt pans flashing white in the sun, and mats that exhale oxygen into air too thin to burn a twig. Inland, braided rivers carry mud into subsiding basins, where it settles into thin, even layers that will one day metamorphose into slates. On continental shelves, red and green shales accumulate. Colors written by ions dance with oxygen and sulfide. Where currents slow, carbonate platforms precipitate thick stacks of limestones and dollostones. Where vents roar, silicious crusts rim black chimneys. What you cannot see is as important as what you can. The nitrogen cycle hums with microbes fixing N2 into ammonia and nitrate. The sulfur cycle toggles between sulfate in surface waters and sulfide below. The phosphorus cycle throttles productivity as rivers deliver pulses from weathered rock. These cycles are linked. Change one and the others adjust. The stability of the boring billion is born from these interlocked gears. It looks flat only when you zoom too far out. The signals future scientists will extract from these rocks are already recording. Stable isotopes of carbon in carbonates swing within a narrow band, a signature of balanced organic burial and volcanic outgassing. Sulfur isotopes in pyrites carry hints of local euxinia on shelves. Iron speciation in mudstones distinguishes ferruginous deep basins from oxygenated shallows. Zircons in sandstones carry uranium clocks that tick with precision, dating sediment sources and orogeny pulses. Paleomagnetic declinations fix paleolatitudes and test supercontinent reconstructions. The data to rebuild this world accumulates grain by grain as rivers spill and seas rise. There is a human thread here too. The ores and minerals that later civilizations will mine are being concentrated. Layered intrusions crystallize chromite and magnetite. Sedimentary basins trap metals in shales. Hydrothermal systems charge veins with copper and zinc. When you hold a modern phone, parts of it were precipitated in a Proterozoic sea or cooked in aproterozoic magma. Deep time is not distant, it's embedded in tools. This is Earth at 1 billion years, stable on the surface, dynamic beneath, oxygenated at the top of the sea, anoxic below, continents converging, mountains rising, rifts cracking, cells busy with internal revolutions that will later surface as bodies and behaviors. In the next part, we'll drop into 3 arenas to make this world tangible. A Grenville mountain front where crust thickens and rivers feed inland seas. A shallow carbonate platform where microbial cities farm sunlight. And a deep basin where iron keeps the night and microbes farm chemistry. Each is a laboratory where physics writes biology into stone. Walk to the edge of a growing continent and the ground tells a story in layers. At the mountain front of the Grenville orogeny, crust thickens under compressive force. Rocks once buried at modest depths are shoved downward, heated and squeezed until new minerals grow, garnet, kyanite, sillimanite, forming banded gneisses with a satin sheen. Fluids migrate through fractures and seed veins of quartz and feldspar. High above those deep reactions, weather chews at peaks and sends a slurry of sand and silt down slope. Rivers braid across broad foreland basins, building deltas where they meet shallow epicontinental seas. Each flood lays down a sheet of sediment. Each dry season cracks mud into polygons that will, millions of years later, harden into the signature of vanished air. Far inland, a different drama punctuates assembly. A rift tears at the heart of the continent and then fails. For a few tens of millions of years, around 1.1 billion years ago, the Midcontinent Rift opens a gash that arcs from what will become Kansas through the future Great Lakes into Canada, pouring out thick stacks of basaltic lava and intruding copper-rich magmas. The rift never reaches the ocean, but it leaves the Keweenawan rocks and native copper deposits that later peoples will mine by hammer and fire. Supercontinents are stitched from collisions and seamed by scars. Both kinds of features lock metal into the crust. Follow those Grenville-fed rivers to the coast and step onto a carbonate platform, hundreds of kilometers of warm, calf-deep water shaded by a hazy sky. The bottom is a living carpet. Microbial communities baffle currents into ripples, trap silt, bind sand, and precipitate minerals. Stromatolites rise as layered domes, some smooth like inverted bowls, others columnar with mushroom caps, where flow and sediment supply change. Their laminae are environmental calendars. Micro-layers track daily growth and nocturnal rest. Bundles group into fortnightly pulses that mirror spring-neap tidal cycles. Thicker beats record seasonal swings, and longer, subtler rhythms tied to precession and obliquity. When the tide falls, fenestrae, gas escape pores, open in the mat and later fill with sparry calcite, a mosaic of white fans that future geologists read as sunset and air. Between shoals, ooids nucleate, millimeter beads of lime rolled by waves, coated layer by layer like pearls around a grit. Tidal channels sort them into dunes that migrate andrew-work, a slow motion captured in cross-bedded limestone. Elsewhere, quieter ponds concentrate brines under dry winds, precipitating gypsum and halite that will later recement into evaporite nodules. Dolomite forms when magnesium-rich waters percolate through soft muds and swap M for K in carbonate lattices, hardening the platform and leaving clues to ancient fluids in its crystal chemistry and isotopes. Biology leans into chemistry here. Cyanobacteria sculpt the mats and pump oxygen into an aqueous film only centimeters thick. That thin lens, the oxygenated canopy over an anoxic column, hosts a caste of early eukaryotes. Acritarchs, organic walled resting cysts with spikes and ornaments, settle from plankton blooms, their silhouettes preserved as tiny inks. Red algal lineages akin to Bangiomorpha lay filaments across mats, dividing with rhythmic regularity that hints at sexual cycles. Gene shuffling becomes a quiet engine. Innovation spreads through populations not only by mutation, but by recombination. Slide off the platform edge and the water darkens. A few tens of meters down, the chemocline marks a boundary between oxygenated surface and anoxic deep. Below, iron rules. Ferruginous waters transport dissolved Fe2+ that never survives in modern oxygenated seas. Where organic matter rains from the sunlit zone and decomposes, microbes switch from oxygen to other electron acceptors. Sulfate reducers, if sulfate is available, make hydrogen sulfide. Along some shelves, that sulfide accumulates in wedges of euxinic water that poison higher life and trap trace metals. In deeper basins, iron reacts with reduced sulfur to make pyrite, locking isotopic stories into black shales. The molybdenum and uranium content of those shales will one day calibrate redox balance across entire oceans. Thereon speciation will fingerprint whether the deep was ferruginous or sulfidic when the mud fell. Hydrothermal vents pepper the seafloor near ridges and intrusions, exhaling hot, metal-laden fluids. As the fluids mix with cold seawater, iron and silica precipitate as shimmering flock and chimney skin. Microbes harvest chemical gradients here, sulfide to sulfate, ferrous iron to ferric, building communities that ignore the sky entirely. In a low-oxygen world, such metabolisms aren't just curiosities, they are pillars that move elements through the crust-ocean biosphere circuit. Pan up to the atmosphere, and a different kind of stability becomes clear. Oxygen holds at low but non-zero levels for long spans. Methane seesaws under microbial control. Carbon dioxide buries itself in carbonates and organic matter, as fast as weathering and volcanoes feed it. Fires cannot take hold on land. The oxygen budget won't allow it. Lightning still flashes, but dry vegetation smolders and cools. The carbon isotope curve, the ratio of 13C, 12C, captured in marine carbonates, stays within a narrow band for much of the Proterozoic, a signature of a biosphere and carbon cycle in steady conversation. That boring line masks regional upheavals. Local oxygen oases flare, shelves tip into sulfide, rifts belch CO2, mountain belts exhale phosphorus via weathering and reset productivity. Night falls and the sky steals the show. With the poles less icy and the magnetosphere channeling charged particles, auroral curtains can creep equatorward in some episodes, writing green waves over seas that modern tropics never see. The moon looms larger than today. Its pull bites harder at tides. Ripple marks, tidal rhythmites, and stromatolite laminae capture those beat patterns so precisely that future researchers will count days per month in ancient rocks and derive Earth's slower spin and the moon's recession from stone clocks. Faunas do not stalk these shores, flora do not root across hills. Land remains a mineral surface shaped by water and wind, stained by microbial films in wet places but empty of forests. Yet the preconditions for later conquest accumulate. Soils begin to appear in humid pockets where mats trap silt and organic acids nibble at feldspars, yielding clays. Those clays thicken weathering rinds, help lock CO2 into carbonates and bicarbonate in rivers, and in the long loop prepare a substrate that future land plants will exploit. Across oceans, Rodinia continues to knit. Laurentia, ancestral North America, welds to Amazonia and Kalahari. Australia and East Antarctica sidle into neighbors. Siberia and other blocks jostle for fit on the globe's jigsaw. Paleomagnetic poles recorded in lavas and sediments let modern geologists test these reconstructions. Zirconagers tie sutures to time. When continent arcs collide, arcs compress and thicken, and when the weight grows too much, the lithosphere can drip into the mantle, redistributing mass and heat. That deep circulation modulates volcanism and topography, which in turn throttle climate via weathering. The planet is a feedback machine. Metals and energy get warehoused during this quiet drama. Black shales rich in organic carbon gather in anoxic troughs. Under later pressure and temperature, they will make hydrocarbons. Stratiform copper and zinc line the seams of basins. Banded iron formations, rarer than in earlier eons, still form where ferruginous currents meet oxygenated shelf water. Carbonatites and alkaline intrusions concentrate rare earth elements. Proterozoic geology seeds resources that later species will prize without ever knowing they were born under Adima's sun. A billion-year snapshot ends as it began, with a balance that could have tipped but didn't. Oxygen was high enough to sustain eukaryotes, but too low to stoke wildfire or large active animals. Continents were gathered enough to steer monsoons and nutrient loops, but not yet locked into their coldest fates. The oceans were stratified, redox stressed below but productive at the lighted skin. Within that skin, cells rehearsed complexity, nuclei, mitochondria, sex, so that when geography and chemistry shifted in the late Neo-Proterozoic, life could sprint. Shift is coming. Rodinia will rift, new passive margins will sprawl, silicate weathering will bite harder in fresh tropical belts, CO2 will fall, ice will advance. Cryogeny and glaciations will scour and raft boulders to tropical seas. Cap carbonates will drape the melt. Redox will whiplash. Ecosystems will be jolted toward novelty. Then the Ediacaran will paint the seafloor with quilted fronds and discs. and the Cambrian will replace quilts with teeth and burrows. None of that is inevitable from the Proterozoic you've just walked, but all of it is permitted by what was built here: a stable engine, a layered ocean, a patient biosphere. Hold 3 images as you leave this era. First, a Grenville river, milk green with silt, laying down a page of future slate, while a mountain belt thickens silently beyond the haze. Second, a tidal flat of stromatolite cities, each lamina a day, each bundle a tide, a billion-year ledger of light and rest. Third, the dark beneath, ferruginous and rich in chemistry, where microbes wire energy without the sun. This is Earth at 1 billion years, subtle on the surface, radical in its foundations, and the hinge on which later worlds will turn.